Albert Einstein's theory of relativity fundamentally changed how we understand the universe. This revolutionary framework consists of two interconnected theories that redefined our concepts of space, time, and gravity. The first theory, special relativity, was published in 1905. It deals with objects moving at constant speeds in straight lines and introduced two fundamental postulates that challenged our everyday understanding of reality. The first postulate states that the laws of physics are identical for all observers moving at constant velocity. The second postulate is even more remarkable. The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. These postulates lead to extraordinary consequences. One is time dilation. Time actually slows down for objects moving at high speeds relative to an observer. This diagram shows light clocks demonstrating how time passes differently for moving objects. Another consequence is length contraction. Objects actually become shorter in the direction of their motion when moving at high speeds. This effect becomes more pronounced as velocities approach the speed of light. 10 years later, in 1915, Einstein published his theory of general relativity. This extended special relativity to include gravity, but described gravity in a completely revolutionary way. Instead of thinking of gravity as a force pulling objects together, Einstein described it as a curvature of spacetime itself. Massive objects like stars and planets actually warp the fabric of space and time around them. This visualization shows how massive objects create wells in spacetime. The larger the mass, the deeper the well. Objects moving through this curved spacetime follow these curves, which we perceive as gravitational attraction. This explains why objects fall toward Earth. They are not being pulled by a mysterious force, but rather following the natural curves in spacetime created by Earth's mass. This elegant geometric description of gravity has profound implications for our understanding of the universe. These theories have been confirmed by countless experiments and observations, from GPS satellites that must account for time dilation to the detection of gravitational waves from colliding black holes. Einstein's relativity continues to guide our exploration of the cosmos. A fundamental concept in special relativity is the relativity of simultaneity. Events that appear to happen at the same time for one observer may not be simultaneous for another observer moving at high speed. In this thought experiment, lightning strikes two trees simultaneously from the perspective of a stationary observer. However, a passenger on the fast-moving train will observe these events at different times due to the finite speed of light. Einstein's most famous equation, E equals mc squared, reveals the profound relationship between mass and energy. This equation shows that mass and energy are interchangeable, with enormous implications for nuclear physics. In nuclear reactions, a tiny amount of mass converts to enormous energy. Nuclear power plants harness this principle, where the conversion of just 1 gram of matter releases energy equivalent to burning thousands of tons of coal. General relativity reveals that massive objects curve spacetime itself. This curvature causes light to bend around massive objects, creating a phenomenon called gravitational lensing. Light from distant galaxies bends around galaxy clusters, allowing us to see objects that would otherwise be hidden. This effect acts like a cosmic magnifying glass, helping astronomers study the most distant objects in the universe. General relativity predicts the existence of black holes, regions where space-time curvature becomes so extreme that nothing, not even light, can escape once it crosses the event horizon. The diagram shows key regions. The event horizon marks the point of no return, while the singularity at the center represents infinite spacetime curvature, where our current physics breaks down. Einstein predicted that accelerating massive objects would create ripples in spacetime itself, called gravitational waves. These waves travel at the speed of light, carrying information about the most violent events in the universe. In 2015, scientists directly detected gravitational waves for the first time using LIGO detectors, confirming Einstein's century-old prediction. These waves were created by two black holes spiraling into each other over 1 billion years ago. Relativity isn't just theoretical, it has practical applications in everyday technology. GPS satellites must account for both special and general relativistic effects to maintain accuracy. Satellite clocks run faster due to weaker gravity and slower due to their orbital speed. Without relativistic corrections, GPS would accumulate errors of several kilometers per day, making navigation impossible. Einstein's theories of relativity have revolutionized our understanding of space, time, and gravity, with implications spanning from the smallest particles to the largest structures in the universe, and from theoretical physics to practical technology we use every day.